Okay, so the question remains though, how do we actually find the minimum sample size for a proportion confidence interval or a mean confidence interval? We keep it there because we in general have little recourse for finding minimum sample size for a variance or standard deviation confidence interval. This typically comes from only looking at margin of error in the context of symmetric confidence intervals, and that's why we only stick to those two scenarios. But there is a theorem that we can point to that tells us the formula for minimum sample size in the event of a confidence interval for proportion. Namely, our minimum sample size, which we denote with lowercase n subscript min, is p hat times q hat, which in other contexts we would just call 1 minus p hat. It's the same thing. Times the critical value for that margin of error estimate divided by the maximum margin of error squared. So remember that this is for the event in which we're estimating a population proportion with a sample proportion p hat. And how do we get this formula? It's actually not too hard to find this. We essentially are using, so our justification here, is we have the margin of error formula that we discussed in a previous section, where we take this formula involving the point estimate, the sample size, and the critical value coming from the z standard normal distribution, and we solve for n. So there is implicitly here a inequality. So if we replace E with E maximum, then this will give us our E minimum, because they are inversely related. As n gets larger, E will get smaller, and vice versa. And we solve for n. So what we can do is we can start by moving the critical value to the other side. We are fundamentally here just performing some algebraic operations with this equation. And now we have this square root on the right side that we can clear by squaring both sides. Now we have fractions on both sides. So we have a fraction squared equals another fraction. And what we can do in this case is we can take the reciprocal of both sides. So we end up with z alpha over 2 over E max squared equals n minimum over p hat 1 minus p hat. And now we can just multiply both sides by p hat times 1 minus p hat. So p hat 1 minus p hat times z alpha over 2 over the maximum margin of error squared equals the minimum sample size. And that is just the reversed equation for the statement that we gave above, right? And so the idea here then is all we need to find in this case, right? So objective, find the minimum sample size for a subject to estimating P with P hat and a maximum margin of error E max at our desired confidence level. So for example, we could be interested in estimating the proportion of students at a 4-year university who actually finished their degree within 4 years. Now, the name 4-year university does not necessarily mean in general that all students obtain a degree within 4 years of starting their studies there. But let's suppose that we seek a 99% confidence interval for P, the proportion, based on a point estimate P hat equals 0.67, or roughly 2/3, and we desire the maximum margin of error to be 0.01, which is 1%. Then our minimum necessary sample size for this would be n min. We use our formula here. Of course, we need to use the confidence level in order to find the critical value. Alpha is 1%, or 0.01, which means alpha over 2 is 0.005, and that has a corresponding right tail critical value. For the standard normal distribution, we find 0.67 times 0.33. Our critical value is 2.58 divided by 0.01 squared. And if we multiply all that out, as long as we don't want to underestimate, then we find that this is approximately 14,718 students, which seems like a lot, but if you keep in mind that major universities tend to have student bodies on the order of tens of thousands, then this isn't too bad. This might be 2 or 3 major universities. And we can do something similar with mean confidence intervals, regardless of which technique we're using, right? So if we're using a T interval or a Z interval, that only changes our estimates slightly. So for a mean, so minimum sample size for a mean confidence interval, there's 2 versions of this depending on whether you have your standard deviation, your population standard deviation or not, right? So the first being if you don't have it, then you have to estimate it using S. And the formula for this would be the critical value using the standard normal distribution again, times the sample standard deviation divided by, oh, I'm sorry, that's not n, that's supposed to be E, the maximum margin of error, squared. Or if you instead do know sigma, you can just replace S with sigma, and that'll be even better. There are other methods that we can use as a workaround for not knowing sigma, but this one is reliable enough for our purposes. So keep in mind, of course, that all of this is estimation. So there is a small difference in that there is uncertainty. We are always estimating. And the question here that you might have is, why don't we use a T critical value when we're looking in terms of the formula we use in both cases, the Z critical value? And that's because since we're looking for n, we're also looking for the degrees of freedom n-1. So in a sense, we're missing more than just one crucial piece of information here. But because these sample sizes that we're looking for tend to be so large, we could reasonably approximate using the standard normal distribution anyway.